Why do you add salt to an ice cream maker? You have to add salt to the ice. Why did we add salt to the bag of ice when we made our ice cream on Tuesday? It made the ice colder, and you saw that, right? You took the temperature of just the melting ice, and it was close to 0, right? And then when you were finishing your ice cream, you took the temperature of the salty ice water, and it was in the ballpark of minus 10 degrees Celsius. It got colder even though we didn't stick it in a freezer. So this is known as freezing point depression. And this is part of a group of properties called colligative properties. And what that means, colligative properties depend on the number of particles that are dissolved in the solution. It doesn't matter what type of particle. So we used rock salt, which is just salt that's not very pure. It's got other stuff in it besides sodium and chloride, and that's why you shouldn't put it on your food. Could you make ice cream with table salt, sodium chloride? Absolutely, it's going to function in exactly the same way, because what you need is a certain number of particles in the water. It doesn't matter what they are. Colligative properties of electrolytes, like sodium chloride and other ionic compounds, are going to be a little different, because if you take 1 mole of an electrolyte, it's going to make more than 1 mole of ions, right? If I take 1 mole of sodium chloride, that's going to make 1 mole of sodium ions and 1 mole of chloride ions, right? And so the total then is 2 moles of ions, of particles. So salt is going to work better than something like sugar, but you could also do sugar. So vapor pressure lowering is a colligative property. We talked about vapor pressure, and we looked at a closed container, maybe with water in it, and we learned that there was evaporation and condensation, and that at some point these would come to a dynamic equilibrium where the rate of evaporation is equal to the rate of condensation. And then because there's water vapor here, it's going to exert a pressure. We call that the vapor pressure, and it depends only on the temperature of the water. Well, what if we have something else in the water? So here we have little red things in with our blue balls. How does that affect the evaporation? Well, in order for the blue balls to evaporate, they have to be at the surface and have high enough kinetic energy, right? But now there's some red balls at the surface, and so there are not as many blue balls at the surface. Does that make sense? So the rate of evaporation of these blue balls is going to be lower than it was before. So we had evaporation and condensation being equal, and now the rate of evaporation or rate of vaporization got reduced, and the rate of condensation is staying the same. And so eventually these are going to catch up with each other until the rate of condensation equals the rate of vaporization. And the result is we've got fewer gas particles here, and so the vapor pressure is lower. Okay with that? I didn't ask if you cared about it. I know that answer. A more fundamental explanation to this is nature's tendency towards mixing, entropy. And this is really a crazy thing. You could try this at home. It takes a while. But so here, this even looks like a cake plate. So here we have 2 beakers. They could be drinking glasses. One has pure water in it, and one has a concentrated solution, maybe a very, very salty water, right? And if we just leave these, and we come back, might be hours later, we'll see that the level of liquid in the concentrated solution container has gone up, and the level of liquid in the pure water solution has gone down. And nobody snuck in here and moved water from one to the other. The water did travel through the air to over here. The rate of evaporation here is higher than it is over there. We're going to eventually get to an equilibrium pressure up here, vapor pressure, and we're going to have less evaporation here, but the same amount of condensation, and so we get a net transfer of water from one beaker to the other. It's kind of like magic. So this is that mixing, that wanting to spread things out to make things equal. You could think of it as nature doesn't like that this is pure water and that's a solution. It wants them to both be the same concentration. The salt can't move, but the water can. And so the water will move to this other solution, making this more dilute, right? And it'll keep going until really all the water is moved over there. So the vapor pressure of a solution is lower than that of the pure solvent. And this is described by Raoult's law, which says that the vapor pressure of a solution is equal to the mole fraction of the solvent times the partial pressure of the pure solvent. So this is the vapor pressure of the solvent all by itself. This is the vapor pressure of the solution, and this is the mole fraction of the solvent in the solution. So the vapor pressure is directly proportional to the amount of solvent. You can also look at the change in vapor pressure. That one doesn't get used very much. Okay, calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees Celsius is 238 torr. Let's highlight some numbers. We got 25 degrees, this many grams of ethylene glycol, that many grams of water, and this vapor pressure. And they're saying calculate the vapor pressure. So the vapor pressure of this solution is going to be less than the vapor pressure of pure water. This is not something that we can do with unit conversions. This is one that requires an equation. This uses Raoult's law. So Raoult's law was that the partial pressure of the solution is equal to the mole fraction of blanking the solvent. I'm not going to make you memorize this. Mole fraction of the solvent times the partial pressure of the pure solvent. What's our solvent here? We had two things here, ethylene glycol and water. The water. Water's almost always the solvent. So I'm just going to put water in there. That's the solvent. And the vapor pressure of the solution is P solution. That's what I'm trying to find. So the equation tells me I need the mole fraction of water in this solution, and I need to know the vapor pressure of pure water. Well, they gave me the vapor pressure of pure water. 23.8 torr. So that's the vapor pressure of pure water. So what I have to find is the mole fraction. I'm looking for the mole fraction of water in this solution. So I'm looking at moles of water or moles of ethylene glycol. to find the mole fraction of water, moles of water. So I'm looking at moles of water divided by the total number of moles, which is the moles of each part, the moles of the water plus the moles of, I'm going to call him egg, e.g. So there's the big idea of what we're doing, but then we have to do some little stuff to get to that point, right? We need the moles of water, but we were given grams. So 285.2 grams of water. Well, we can convert that to moles of water. We just need the molar mass of water, which, if you don't have it memorized, you can just calculate it real quick. .285.2 divided by 18.02. 15.8268 moles. I'm keeping 4 sig fig here because this starting number had 4 sig figs. So that's moles of water. And then I have the mass of the ethylene glycol, 55.3 grams of EG. So we need to calculate the molar mass of this one. There's hydrogens and carbons and oxygens all over the place. Let's count up the hydrogens. There's 1 plus 2 is 3 plus 2 is 5 plus 1 is 6. So 6 times the mass of hydrogen. And I've got 2 oxygens. 2 times the mass of oxygen. And 2 times the mass of carbon. So 62.07 grams. 1 mole of ethylene glycol, 62.07 grams. Zero 0.8093 moles of ethylene glycol. I picked 3 sig figs here because the starting number had 3. So now we're going to take these numbers and plug them into this equation. So on the top we've got the moles of water. And on the bottom, we have the moles of water plus the moles of ethylene glycol I'm going to have to I know what I can do. Move that up out of the way. So 15.8268 divided by the quantity, 15.8268 plus 0.89093. just gonna move this guy again. Let me come down here. So that's our mole fraction of water, right? So the pressure of our solution is the mole fraction of water times the pressure of the pure solvent. .5 torr. The unit on this pressure will be the same as the unit on the other pressure that we used. Any questions?
So it's the pressure of the solution, and then it's the solvent times the pressure of the solvent?
Yeah, it's the mole fraction of the solvent times the partial pressure of the solvent as a pure solvent. So really this acts sort of like a percentage. The mole fraction tells us in terms of moles, this is 94.67% water. And so the pressure above this solution is going to be 94.67% of the pressure it would be if it was pure water. Any other questions? So that's a situation where the solvent itself was not evaporating. But what if the solute is volatile? Then it will contribute to the vapor pressure of the solution. So what we call ideal solutions are ones that obey Raoult's law at all concentrations. And then we would know that the total pressure above that ideal solution is the partial pressures of the components. The partial pressure of the water plus the partial pressure of the solute. But there are also non-ideal solutions, and these do not obey the rules because of interactions between the solute and the solvent. So this is ideal behavior. What are these funky things? Here we're looking at vapor pressure on the y-axis and partial pressure, mole fraction of A on the x-axis. That's y, this is x, yes. So when the mole fraction of A is 0, then the partial pressure of A is 0. That's the red line. And as the mole fraction of A increases, then the vapor pressure of A will increase until it reaches the pure vapor pressure. When the mole fraction of A is 0, then the mole fraction of B is 1, and so this would be the vapor pressure of pure B. As B decreases, it'll go down to 0 when it's all A. And the ideal behavior is that the sum of these two things is a straight line. These are straight lines, and this is a straight line. If we have strong solute-solvent interactions, so the solute and the solvent really like each other, and so that's going to slow down their evaporation, right? Because they're like busy talking to each other at the surface of the water. Like, I kind of like you, and what are you doing Tuesday night, right? And so then they're like, oh, wait, I was supposed to be evaporating. So there's less vapor pressure. So as we increase the mole fraction, as it gets more mixed, then the vapor pressure of each of those components is a little smaller than predicted because they're hanging out too much. And so then the sum of these is also going to be lower than expected. Or we could have the opposite situation where the solute and the solvent really do not like each other. And so they're at the surface, and it's like, well, normally I would evaporate like this, but ooh, I don't like you. I'm going to get out of here as fast as I can, right? And so then the vapor pressure of each component is going to be a little larger than it would be if it was behaving ideally, and so the total here is going to bulge up. Any questions? This question, this example, is what some might describe as a mind flog. And there's multiple parts to it. And honestly, I don't think it's worth our time to go over that. There is at least one homework question that is going to do stuff like that. But I won't ask you a question like that on an exam. It's just, I think that's just overboard. So let's just go on and talk about freezing point depression and boiling point elevation. So here we're looking at a phase diagram for water, and so the blue line represents where the transition is between liquid and solid, liquid and gas for pure water. And when you add a solvent, that's going to lower the vapor pressure of the solution. And so the pressure is going to be lower here for all of this. And as a result, the boiling point becomes, sorry, that's not the boiling point, the freezing point gets lower and the boiling point gets higher. I used to have a hard time remembering, was it freezing point depression or freezing point elevation? Because there's boiling and freezing, and there's elevation and depression. So what helps me remember this is that these are moving away from each other. The boiling point's getting lower, and the freezing point is getting lower, and the boiling point's getting higher. They're moving away from each other. Here is a picture of someone putting antifreeze into the radiator of his car. Why do we do that? That's ethylene glycol, usually. There are other types of antifreeze. But adding a solute to the water in your radiator lowers its freezing point, which, in Central California, we don't really need to worry about that. And it raises the boiling point. That's something we would care about. You don't want your radiator to freeze, because obviously it's not going to function, but also when the water freezes, it expands, and it's going to make a mess of your engine. It'll break your radiator. And then you don't want it to boil either. That's when your engine is overheating and you get steam coming out of the front. So the vapor pressure lowering means that the melting point or the freezing point is lower and the boiling point is higher than for the pure solvent. So this is the equation for freezing point depression. The change in the freezing point is equal to the molality times the freezing point depression constant. And this, these two equations are really the only reason why we really need to talk about molality. We use molality here instead of molarity because molality doesn't change with temperature, molarity does. So molality is always used for this. Kf is a constant that you look up or they give you on a problem. Delta Tf, the change in the freezing point, as it says there in parentheses, is usually reported as a positive number, which kind of breaks all the rules because this should be the final minus the initial. It should be a negative number, but it isn't. I don't know why they do that, but we just have to deal with it. So here are some freezing points and boiling points and the associated constants for several different solvents. Water's down here, freezes at 0 Celsius. The freezing point depression constant is 1.86. The units are degrees Celsius per molal. Normal boiling point 100, and the boiling point elevation constant is 0.512 degrees per molal. So calculate the freezing point of a 2.6 molal aqueous sucrose solution. So we need this constant here, 1.86, for our freezing point depression constant. So Kf equals 1.86 degrees Celsius per molal. So they gave us a molality, and they're asking for the freezing point. So we had that equation. The freezing point depression is equal to the molality times the freezing point depression constant. Well, they gave us the molality. Yay! 2.6 molal. And we looked up the constant, 1.86 degrees Celsius per molal. We had an equation, we put numbers into it, we got an answer. It's very tempting to say, well, this is the answer to the problem. But it isn't. This is the change in the freezing point, the freezing point depression. So if we think of a thermometer, let's see if I can draw a decent thermometer. So if that's 0 degrees Celsius, and up here's the boiling point of water, this tells me that the freezing point has gone down 4.8 degrees Celsius. So my new freezing point is less than what it was before. And this difference here is 4.8 degrees Celsius. So what is the new freezing point? Negative 4.8. And that's the trickiest thing about these calculations. You calculate the change in the freezing point, but then you have to relate that to the freezing point of the original thing. Any questions? Boiling point elevation. The equation looks remarkably similar. The change in the boiling point is equal to the molality times the boiling point elevation constant. So the antifreeze not only prevents your radiator from freezing, it also prevents the water from boiling, which is also a good thing. So, very similar calculation. Calculate the boiling point of a 3.6 molal aqueous sucrose solution. So we're going to need the boiling point elevation constant, which for some bizarre reason I happen to remember. There it is. They gave me the molality again, and this time they're asking for the boiling point. This is an aqueous solution. Water is the solvent, right? We just kind of skipped over that and assumed that in the last problem. So the change in the boiling point is going to equal the molality times the boiling point elevation constant. 3.60 molal times 0.512 degrees Celsius per molal. 1.8432 degrees Celsius. And again, that's not the answer. Because adding something to your water is not going to make it boil at 1 degree Celsius. This tells me that it's changing the boiling point. The boiling point's going up. The boiling point goes up, the freezing point goes down, they move away from each other. So this difference here is going to be 1.8 degrees Celsius. So that's 100 plus 1.8, and the new boiling point then is going to be 101.8 degrees Celsius. Any questions? This is the kind of calculation that we're going to do for our ice cream lab. Why does it say 0.84? Because I was sloppy. This has 3 sig figs, and that has 3 sig figs, right? So. On a multiple choice test, you just need to know, okay, this is the closest one, right? Osmosis is a word you've probably heard. Osmosis is the flow of a solvent from a solution with a lower concentration of solute to one of higher concentration of solute. And this is the process by which seawater causes dehydration. The flow of solvent here is going to happen through a semi-permeable membrane. So it's semi-permeable. It's permeable to some things and not others. It will allow things like water to pass through, but not other things like the solutes, like maybe sugar or salt. So biological cells contain semi-permeable membranes, and so osmosis is a big deal for biology. In chemistry, we can set this up using a U-shaped tube. I used to call those U-tubes, but that's something else now. So the osmosis cell has this U-shaped tube, and there's a separation in here, this semi-permeable membrane. On one side of the tube is pure water, and on the other side of the tube is a solution, maybe salt water. So what happens is osmosis occurs and the water flows from one side to the other through this semi-permeable membrane. And the result is that the liquid level rises on one side and goes down on the other side. If you remember back to the chapter on gases, we would have things like this, and we look at the pressure difference. And so we can measure the difference in height of these columns, and that would be the pressure difference in, say, millimeters of water. That's a pressure, and that is what is called the osmotic pressure. That is the pressure you would have to apply to this side to stop the osmosis from happening. Reverse osmosis, which is one way to purify drinking water, is when you apply a lot of pressure here and you force the water to go through that semi-permeable membrane, and so you can keep the contaminants over here and get the pure water to go through. How exactly is this happening? Well, the semi-permeable membrane allows water molecules to go in both directions, and so they will. But again, we're going to get an equilibrium set up eventually, the solute particles over here are kind of blocking the access to this semi-permeable membrane, and so they're going to reduce the rate at which water molecules move from the left to the right. There's no such blocking on the right, so water molecules moving from right to left, there's going to be more of those. And so that's one way of understanding what's happening here. Another is just, nature doesn't like things to be different. And so this is a concentrated solution, and this is not at all concentrated, and it's like, okay, we got to mix this up, and it's going to do what it can. So osmotic pressure has an equation too. Of course, you have to have an equation for everything. This one's a little different. So here, that capital M is the molarity of the solution, T is the temperature in kelvins, and R is the ideal gas constant. So we are talking about pressure, and so these are units that we used when we were talking about pressure of gases. And this is a capital pi, if you're not sure what that is. So we can calculate the osmotic pressure in atmospheres of a solution containing 1.50 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. So we need the equation. So the osmotic pressure, capital pi, is equal to the molarity times the ideal gas constant times the temperature. I write that down before I forget it. Let's highlight what we know. We've got a mass of ethylene glycol, we've got a volume of solution, and we have a temperature. So we have 1.50 grams of, I think the formula's shorter this time, ethylene glycol. We have 50 milliliters of solution, and we are at 25 degrees Celsius. We're supposed to calculate the osmotic pressure. Osmotic pressure in atmospheres. So we're going to use this equation, and it's set up to calculate the osmotic pressure, but we need to know the molarity, the ideal gas constant, and the temperature in kelvins. So the ideal gas constant is going to be 0.08206 liter atmospheres per mole times Kelvin. We can convert our temperature to Kelvin. And then we need to calculate the molarity of this solution. So there's molarity again. We need the moles of the solute, and we need to divide by the volume of the solution in liters. So we can convert this to liters. So that's going to be 10 to the minus 3 liters. So we're going to get 0.0500 liters. And then we're going to need the molar mass of this. So that's going to be 2 times carbon plus 6 times hydrogen plus 2 times oxygen. $62.07. $62.07 grams per mole of this ethylene glycol. So this gives us 0.024166 moles. And so then we can calculate the molarity, moles of solute divided by liters of solution, So now we have all the pieces. So the osmotic pressure is going to be the molarity we just calculated, 0.48332 moles per liter, times, there's not going to be enough space. Let's bring this guy down here. Times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. Guy always takes up so much space. And the temperature. So looking at the units here, moles cancel with moles. And liters cancel with liters. And the kelvins cancel, which leaves us with atmospheres. So 0.48332 times 0.08206 times 298. 11.819, 11.8 atmospheres. It's actually a pretty high pressure, almost 12 times normal atmospheric pressure. Any questions?